My name is Mike Kahn, David Game College, London. I teach chemistry to A-level students, have done so for over 30 years. So many students find chemistry abstract, difficult, very user-unfriendly. And I'm going to show you now we can make chemistry much simpler by looking beyond the subject for everyday analogies, relevant analogies that help us to understand concepts which can be tricky. And no concept causes chemists more headaches than the mole. So to get around these problems, what I'm going to do is to do a simple experiment involving two coins, a pound coin and a 5p coin. I'm going to weigh the heavier coin, the pound, a reading of 9.60 grams. I'm now going to weigh the lighter coin of the two, the 5p coin. Let's make sure our balance is stable. And that gives us a mass of 3.30 grams. So if I now divide the mass of the pound coin, 9.60, divided by 3.30, we find that to two places as decimals, we get a ratio of 2.91. In other words, the pound coin is roughly 3 times as heavy as the 5p coin, just under 3 times as heavy. Now let's find two other objects, only this time not objects we can look at and feel and touch and understand, but a copper atom, copper, and a tungsten atom. Tungsten is the metal filament inside this light bulb. And of course we haven't just got one atom here, we've got billions and billions of atoms. But if we go to our periodic table and look at the relative atomic masses shown at the top here on each sheet, the relative atomic masses, if we compare them, divide the bigger number for tungsten, 183.8, by the smaller number, 63.5 relative atomic mass of copper, we will find out in exactly the same way as we did with the coins how much heavier a tungsten atom is, that is a single tungsten atom, compared with a copper atom. So we divide the bigger number by the smaller, and we find that we get a virtually identical result, 2.89, 2 decimal places, again just under 3 times. So we have this similar ratio. Now that means if we were to weigh out exactly those quantities, 183.8 grams of tungsten and 63.5 grams of copper, in each sample we would have an identical number of atoms because the ratio is correct. Now the number of atoms in each pile is going to be astronomical, far too large a number for us to comprehend. But physicists are very clever people, and using experiments involving oil drops, charged oil drops, which we don't need to go into here, they've been able to determine exactly what that number of atoms is in 63.5 grams of copper or 183.8 grams of tungsten. And that number, massive as it is, they can determine, and we know it to be 6.02 times 10 to the power 23. We give it the name of 1 mole, sometimes also known as Avogadro's number, Avogadro's constant. But what is it? It's just a number, albeit a very large number. But you shouldn't be intimidated by it, because we also know from everyday life, beyond chemistry, that 1 dozen means 12. It doesn't mean 12 grams or 12 centimeters, it just means 12. In the same way, 1 mole is just a number. Why do we need this number? Well, to understand that, let's do one final experiment, also involving coins. Now here I have a large number of 2p coins. Let's weigh the whole sample. That's what banks do. They count coins by weighing, not by going 1, 2, 3, 4, etc. So we put all our coins on the balance, the whole sample. It's quite a large number of coins. And we find that we have a total mass of 300.5 0.9 grams. That's all our 2p coins together. Now if I remove all the coins, we ask ourselves a simple question: how can we find out by weighing, not by just counting laboriously all the coins, how many coins we've got here? What we could do is just leave one coin on the balance, like so, weigh that, divide the larger number by the smaller, we'll know how many coins we have. But that's all very well for coins. But when we're counting atoms, if we were to do that, we'd get a ridiculously large number. So let's group them. Instead of counting an individual coin, let's group them in 12. So let's put on the balance, let's put the second one back, plus another 10. So I'm now going to weigh 12, exactly 1 dozen 2p coins. And I get an answer 85.74 grams. I will divide the larger number, that's the mass of all those coins that we put on originally, by the mass of 1 dozen coins, 85.74. And I get the answer, to one decimal place, 3.5 exactly. And that's quite interesting because if we look at the result again in its entirety, we can see that what we've been doing is counting not how many coins there were there, but how many dozens of coins, because we grouped them in 12s. And we divided the total mass of all the coins by the mass of 12. We get the answer 3.5, in other words 3.5 dozen, and there were indeed 42, 3.5 times 12, 10, 20, 30, 40 plus 2, 42 coins. Finally, why don't we do that with atoms? Because if we grouped our atoms in 12s, then we'd still get a ridiculously large number. So instead of grouping them in 12s, what we do is we group them in moles, 6.02 times 10 to the 23 atoms at a time. So we have now a formula that everyone recognises but maybe didn't understand before. Number of moles of atoms in any sample is the total mass of the sample in grams divided by the mass of 1 mole of atoms. And we can broaden that out to include any other substance, even if it's not made of atoms. Number of moles of a substance equals mass of substance in grams divided by the molar mass. But the important thing to understand here is 1 mole is not a mass of anything. It is a number, and all we're doing is we're using weighing to count, which is all the banks do. And that is all the mole concept is all about.